Hi, and welcome to day 25 of Just Start Programming, the Rust programming language. Today, I would like to spend more time on the interior mutability pattern and reference cycles. Once again, this is not a tutorial, but if you are curious to learn this together with me, then please stick around. So join me once again, do it live in one take, no shortcuts, no secrets. Let's just start programming. Yep. So the other day, I think we need to revisit and learn more about interior mutability once again. Because I admit I didn't quite understand everything. So for the purpose of really learning what is presented here in the book, so let's go through it once again. But before that, interior mutability, let me just quickly refresh my memory. We have this reference counter. So it keeps track of the number of references. So we have this diagram where we have const. I think the key information here is that if we just use it as it is, this one will generate a compilation error. And what we need to do here is, instead of box, we can make use of reference counter. Yeah, reference counter. Here. Instead, we'll change our definition of list to use reference counter in place of box. Each const variant will now hold a value and a reference counter pointing to a list. One more information we need to take note is that we'll also clone. So there's a clone function that is being called here to the reference. But cloning, I think there was something here that is important. Here, RC clone doesn't make a deep copy. So it only increments the reference count, which doesn't take much time. So it only increments the reference count. When looking for performance problems in the code, we only need to consider the deep copy clones and can disregard calls to RC clone. So there won't be any performance impact. Okay. So cloning here, as demonstrated, increases the reference count. I think we had a code yesterday here. So RC new const 5, RC new const 10, and RC new nil. And then there's a count here, strong count function, to display the reference count of A. And then Here we experimented a little bit, so we kept B within the scope. Here we are checking reference count of A, strong count function. And then here, let C is constrained to this scope, so that over here, if we count after C, then C goes out of scope. This one will reduce the count of reference count of A. Then here, B goes out of scope, so this one will reduce the reference count further. But what we were not able to get a count of A, which is I wanted to have it displayed as 0. I don't think that is possible. So let's run this. There. Count after creating C is 3. But C goes out of scope here, so it's reduced to 2. And B goes out of scope here, it's reduced to 1. Here, count after A is out of scope. Actually, this is not true, because it's only after this that A is going to be out of scope. So we're down to still 1 here. Okay, so that is just a quick review. And over here, let's start again with a fresh mind and see what is this interior mutability. Okay, so it's a design pattern that allows you to mutate data even when there are immutable reference to that data. So even if there's immutable reference to that data, it allows you to mutate data. That's interior mutability. So normally this action is not allowed by borrowing rules to mutate data. The pattern uses unsafe. So it's unsafe code inside a data structure to bend Rust usual rules that govern mutation and borrowing. Unsafe code indicates to the compiler that we're checking the rules manually instead of relying on the computer to check them for us. We will discuss unsafe code more in chapter 20. We can use types that use the interior mutability pattern only when we can ensure that the borrowing rules will be followed at runtime. So, interior mutability pattern only when we can ensure borrowing rules will be followed at runtime. So it's the programmer who is supposed to be enforcing this rule, because now this won't be checked at compile time, even though the compiler can't guarantee that. The unsafe code involved is then wrapped in a safe API, and the outer type is still immutable. So it means that the unsafe code is going to be wrapped in a safe API. What is this API? And the outer type is still immutable. So the concept is using this reference. What is cell again? Reference cell. What is it cell? Interior. Okay. So ref cell is the interior mutability pattern. How do we enforce it? Enforcing borrowing rules at runtime. Unlike RC, the ref cell type represents single ownership. So this one is only single ownership over the data it holds. So what makes ref cell different from a type box? Recall the borrowing rules you learned in chapter 4. Okay. At any given time, you can have either one mutable reference or any number of immutable references, but not both. You can have only one mutable reference or any number of immutable reference, but you cannot mix both of them. References must always be valid. With references and box T, the borrowing rules invariants are enforced at compile time. So it is enforced at compile time. With ref cell, these invariants are enforced at runtime. Okay, so this one is enforced at runtime. With references, if you break these rules, you get compiler error. Yes. With ref cell, if you break these rules, your program will panic and exit. So since it is runtime, if you break these rules, your program will panic and exit. So at this point, here we can do some error handling. But if it's compile time, then you cannot compile the code. You're forced to fix the issue. The advantages of checking the borrowing rules at compile time are that errors will be caught sooner in the development process, and there is no impact on runtime performance because all the analysis is completed beforehand. Yeah. So because it's being checked at compile time. For those reasons, checking the borrowing rules at compile time is the best choice in majority of cases, which is why this is Rust's default. So far, we are following the borrowing rules because at compile time we encountered errors. The advantage of checking borrowing rules at runtime, so this time it's at runtime, instead is that certain memory save scenarios are then allowed, where they would have been disallowed by compile time checks. But what are those scenarios? Static analysis like Rust compiler is inherently conservative. Some properties of code are impossible to detect by analyzing the code. Okay, so there's still a possibility that the compiler cannot detect. The most famous example is the halting problem, which is beyond the scope of this book, but is an interesting topic to search. Okay, yesterday we just searched halting problem, but at this point in time we don't know. We don't want to learn about halting problem. Yeah. Because some analysis is impossible, if the Rust compiler can't be sure the code compiles with the ownership rules, it might reject a correct program. Yeah. So although your program is correct, because of the what is this? Ownership rules, the code compiles with the ownership rules. Okay. If the Rust compiler can't be sure the code compiles with ownership rules, it might reject. Okay, so by default it is conservative. If Rust accepted an incorrect program, users wouldn't be able to trust in the guarantees Rust makes. Then again, it's conservative. However, if Rust rejects the correct program, the programmer will be inconvenienced. But nothing catastrophic can occur. Okay. Yeah, that is if the programmer is already an expert level, I guess. The ref cell T type is useful when you're sure your code follows the borrowing rules, but the compiler is unable to understand and guarantees that. Okay, so ref cell This is one of the use case because it's useful when you're sure your code follows the borrowing rules. But the compiler is unable to understand and guarantee that. So you can use refcell. Similar to RC, refcell is only for use in single-threaded scenarios and will give you compile time error if you try using it in a multi-threaded context. So refcell can only be used in single-threaded scenarios. Refcell has something to do with runtime. And then, what else? What else is there? Yeah, so it's at runtime, single-threaded. We'll talk about how to get the functionality of refcell in multi-threaded program in chapter 16. Okay, next chapter. Here's a recap of the reasons to choose boxt, RC, or refcell. RC enables multiple owners of the same data. So going back to the analogy of watching a TV program in the living room. So there's a reference counter. There's no performance impact. All it does is counting the one referencing the data. boxt and refcell have single owners. boxt have a single owner, refcell have a single owner. Okay. boxt allows immutable or mutable borrows checked at compile time. So boxt is at compile time. RC allows only immutable borrows checked at compile time. So RC and boxt at compile time. RC only allows immutable borrows, while boxt allows immutable and mutable borrows. Refcell, however, allows immutable or mutable, so both immutable or mutable borrows checked at runtime. So you have more flexibility here, but it is done at runtime. So the programmer is the one responsible to ensure that the borrowing is correct. What's the term there? Borrowing rules should be correct at runtime. Because refcell allows mutable borrows checked at runtime, you can, okay, so why mutable? Because it is both immutable or mutable. Mutable borrows checked at runtime, you can mutate the value, so you can change the value inside refcell even when the refcell is immutable. So if refcell is immutable, you can mutate the value inside. So maybe that's where it got its term. Yeah, here. Mutating the value inside an immutable value is the interior mutability pattern. So what is interior mutability pattern? It is allowing you to mutate the value inside an immutable value. Okay, let's take a look at a situation in which interior mutability is useful and examine how it's possible. Mutate a mutable borrow to an immutable value. Okay. A consequence of the borrowing rules is that when you have an immutable value, you can't borrow it mutably. For example, classic case. X is equal to 5, so this is in stack. Here, X, you have a reference to a mutable X binded to Y. If you tried to compile this code, you'd get the following error. Cannot borrow X. Yeah, so because here you have ampersand, so you cannot borrow X as mutable, and it is not declared as mutable here. So here, over here, it's immutable. So the suggestion of the compiler is to make X as mutable. Okay. However, there are situations in which it would be useful for a value to mutate itself in its methods. Mutate itself in its methods, but appear immutable to other code. Code outside the value's methods would not be able to mutate the value. So that one sounded like a private function. I mean, kind of sound like a private function. Using ref cell is one way to get the ability to have interior mutability. But ref cell doesn't get around the borrowing rules completely. Okay, the borrow checker in the compiler allows this interior mutability, and the borrowing rules are checked at runtime instead. Okay, so at compile time, it is allowed. But at runtime, the borrowing rules are checked. Yeah. So it means that if the developer, the programmer, does not follow the borrowing rules, at some point in the runtime, it will panic. The program will panic. If you violate the rules, you get a panic. Yeah, here, instead of a compiler error. Let's walk through a practical example where we can use refcell to mutate an immutable value and see why that is useful. Okay. So here, a use case for interior mutability, mock objects. This was the use case we were reading yesterday. Sometimes during testing, a programmer will use a type in place of another type in order to observe particular behavior and assert that it's implemented correctly. This placeholder type is called a test double. Think of it in the sense of a stunt double in filmmaking, where a person steps in and substitutes for an actor to do a particular tricky scene. Test doubles stand in for other types when you're running tests. Mock objects. So mock objects are like test doubles. So these are specific types of test doubles that record what happens during a test, so you can assert that the correct actions took place. Rust doesn't have objects in the same sense as other languages have objects, and Rust doesn't have mock object functionality built into the standard library, as some other languages do. However, you can definitely create a struct that will serve the same purpose as mock object. Here's a scenario we'll test. We'll create a library that tracks a value against a maximum value and sends messages based on how close to the maximum value the current value is. This library could be used to keep track of a user's quota for the number of API calls they are allowed to make, for example. Our library will only provide the functionality of tracking how close to maximum a value is and what the message should be at what times. Applications that use our library will be expected to provide a mechanism for sending the messages. Okay. So here, our library will provide tracking, how close to the maximum value, and the message that is sent should be sent at what times. So it's the other applications using our library to provide the mechanism for sending messages. The application could put a message in the application, send an email, send a text message, or do something else. The library doesn't need to know that detail. All it needs is something that implements a trait we'll provide called messenger. Okay. Let's see if we have this in our code. Not yet. So let's copy this one first. We have a trait called messenger with the function send, reference to itself, and the message, which is slice string. Next, there's a struct. There's a struct called limit tracker, and this one is the lifetime. And then you have type T, which is messenger, this one, the trait. Then messenger, you have a reference to T, and this one is the lifetime. Okay, you have value use size and max use size. Okay, so this is a long one. Okay, so we have an implementation of limit tracker. Wherein limit tracker is the struct, where T, okay, so where T is messenger trait. So pub function new, you have messenger, okay, so referencing T, which is the trait messenger. And then you have, okay, so the apostrophe is A, they have the same lifetime, max use size, and it will return a limit tracker with this lifetime, wherein T is messenger. Limit tracker messenger. Limit tracker will have the messenger trait itself, the value, and then the max. Then there's another public function set value, a mutable reference to self, and then the value. So self.value of limit tracker equals value here that is passed to the parameter. Then percentage of max, which is a floating point, 64 bit. You have self value as, okay, as this one, data type, divided by max as a floating point value also. If percentage is greater than equal to 1, then it shows you are over your quota. So messenger send. Where is send? Send is over here. So it's part of the trait. Send. But where's the implementation? Let this compile. Send to self, and then you have the message. Okay, send, you have the message here. Else, if percentage of max messenger send urgent warning. There's something a bit strange here. I don't know if you noticed that. So here there's this %t. How about if we move down send this? Okay, now they look the same. Now they look the same. Okay. Percentage of max is greater than equal to 75, then you've used up over 75% of your quota. Okay. Let's see the analysis here. An important part of this code is that messenger trait has one method called send. That takes an immutable reference to self. Immutable reference to self. Yeah, because there's no mut here. Immutable, so this is immutable reference to self. And the text of the message. Text of the message is here. So this one is also immutable. This trait is the interface our mock object needs to implement so that the mock can be used in the same way as a real object is. The other important part is that we want to test the behavior of the set value method on the limit tracker. We can change what we pass in for the value. Okay, so we can control, because we can change the behavior here based on the value. As you can see, value is being used. So it will compute the percentage. Okay. But set value doesn't return anything for us to make assertions on. So there's no return here. So you cannot check from set value. The only thing it can do is it can send a message like this. Yeah, it can send a message. But who is implementing the message? Because this is a trait here, we only define the signature of the function. So how the function will look like. But the one who is using our library will be the one implementing the send. So I think it was mentioned somewhere here. Okay, the application could put a message in the application, send an email, send a text message, or do something else. Because applications that use our library will be expected to provide the mechanism for sending the messages. So here, the contract is defined, but eventually the application using this trait is the one sending an email or send a text or do something else. In which the library doesn't need to know the detail, this library. Okay. So this is immutable, this is immutable. At this point, it is immutable, nothing has changed. Okay. The other important part is we want to test the behavior of setValue method on the limit tracker. We can change what we pass in for the value parameter, but setValue doesn't return anything for us to make assertions. We want to be able to say that if we create a limit tracker with something that implements the messenger trait and particular value of max, when we pass different numbers of value, the messenger is told to send the appropriate message. Particular value for max, yeah, because self max, particular value of max here in the limit tracker. It's a combination of value and max. So value and max. Then it will go through this if-else if statement and call this send function and have these values in the message. Yeah, in the message here. Okay. When we pass different numbers of value, the messenger is told to send the appropriate messages. We need to mock object. We need a mock object that instead of sending an email or text message when we call send, will only keep track of the messages it is told to send. So here's the part where we need to create a mock object. So we're assuming that somebody is implementing this library or making use of this library. We can create a new instance of the mock object, create a limit tracker that uses the mock object, call the setValue method on the limit tracker, and then check that the mock object has the message we expect. So listing 15-21 shows an attempt to implement a mock object. To do just that, but the borrow checker won't allow it. Okay, so let's copy this one. So it's like we're implementing the library, and it should be in lib.rs. Oh, wait. Oh, this should have been in lib.rs. My mistake. So let's change the code a little bit. Let's create lib.rs here. And then from main, let me just move this over there. Cut. Okay, and then copy this one. Let's see. So this is how we can create a test configuration, and then we have test cases. Here's the test case. Yeah, here's the test case. It sends an over 75% warning message. Okay, so usual, use super, asterisk. Here we are creating a new struct, which is mock messenger. Yeah. Mock messenger, because eventually we wanted to implement this messenger. So this is not the real messenger, it's the stunt double. This is the mock object, mock messenger. So inside mock messenger, you have a way to send messages, and we need to keep track of the message by using vector. And here we are implementing the struct mock messenger. So we'll create a new constructor. It will return mock messenger, which is a mock messenger struct containing sent messages, where the vector macro initializes the vector, which is at this point in time it's empty. Then we implement messenger. So messenger is the trait for mock messenger, and because we're implementing a trait, so if you sometimes it's not good to copy and paste, but if we comment this out, you will see that we need to implement not all trait items implemented missing. So send you need to implement because it's the contract for this trait which you need to do. I think there's some autocomplete here also. So the quick fix is, there's a quick fix. Quick fix. Here. Implement. There. Yeah. But at this point to do is dummy. So the actual implementation is like this. So let me delete this once again. And here. Okay. So we are implementing send, the same signature, reference to self, which is immutable, and message, which is a string slice. Then self sent message. Where is sent message? Self is a mock messenger. We'll have sent message. Do we have sent message in the library? Nope, I don't have. This is new and set value for the limit tracker. Sent messages that push. What does it do? So it's a vector. So we're pushing, okay, so pushing value inside the vector, which is a string from message. String from message. So what does it actually do? We know that messenger has a send a function. Messenger is a trait. So if, okay, we have limit tracker here. The limit tracker will have messenger. No, the set value for limit tracker will accept value, and then self is at this point mutable. But who is self? Self is limit tracker. No, the value inside is mutable. Value, yeah. Okay, and then limit tracker will call based on the messenger. Okay, so messenger here is who is messenger? Messenger is T. Okay, so messenger is the messenger trait. So the messenger trait will have send. Okay, send, and then the value is passed here. So it's like from here, it will have that Say, for example, warning, if you stop 75% of your quota, then that value is here, message. And how does it make use of the message? It will push it into the vector. Okay. So it will complains. Consider changing this to be a mutable reference. Sent message. Who is sent message? Here. Sent message is not mutable. Sent message is immutable. So it complains. As it is behind a reference self and is a reference, so the data it refers to cannot be borrowed. Consider changing this to be a mutable reference in the IMPL method and the trait definition mat. IMPL method. So where's the IMPL method? Here. Here. So if we change that, can we change it here? Mat. Did it work? Found keyword mat. Oh, expected identifier. No, what? It's not the right place, it seems. Mat. Can we do something like this? Font. Oh, can I put it here? Can we put it here? Not X. Struct mock messenger. Self. Where can we put it? Consider changing this to a mutable reference in the IMPL method and the trait definition mat. Mat. So this one will be allowed at compile time. Why does it suggest it to be mutable? Okay, did it change anything here also? Yeah. Now this is also mutable. Mutable. Okay. So that one will fix it. But we will not be doing that. Let's follow the book. So it means that this is immutable. And self, we are changing the value, because now inside self we have a vector where we are changing the value of the vector. Okay, so let's see. In the test, what happens when the limit tracker is told to set value to something that is more than 75% of max? Value. First, we create a new mock messenger which will start with an empty list of messages. Then we create a new limit tracker and give it a reference to the new mock messenger and max value of 100. Okay, so here mock messenger new mock messenger, then limit tracker, which is mutable, limit tracker new, the referencing mock messenger, so we are borrowing here, and we are setting the value max value to 100. So limit tracker new mock messenger 100. So limit tracker returns a mutable limit tracker new. Okay, so limit tracker messenger, so that is the mock messenger this time. Max value is 100. What's wrong with this? What was the original one? Messenger for mock messenger. Set value. Self value value. Self value value. Self. Okay, this is mut. Okay, only this one is mut. So self is mutable. Okay. And then limit tracker, now this is limit tracker, which is mutable. Set value to 80. So set value to 80. So 80 will be here, urgent warning. No. Warning, you've used up 75% of your quota. Okay. But this one complains. Self-sent message as mutable, as it is behind ampersand reference self and ampersand reference, so the data it refers to cannot be borrowed. So cannot be borrowed. So what can be done here? We cannot modify the mock messenger to keep track of the messages because send method takes an immutable reference to self. Okay, send message takes an immutable reference to self. Yeah, so this one is immutable, so you cannot change this. How about in messenger? Yeah. Okay, because here it's already defined as immutable. Mutable. Okay. We also can take the suggestion from the error text to use %mut self in both IMPL method and the trait definition. We do not want to change the messenger trait solely for the sake of testing. Okay, so it means that since this is provided as a library to fix the issue, it means that we need to change this to a mutable self. But what that means is, yeah, you put MUT here. And we don't want to do that because for the sake of testing, it says that you're changing the library also. So it can be done here. Instead, we need to find a way to make our test code work correctly with our existing design. So it means that we will not change the library. This is a situation in which interior mutability can help. You'll store the sent messages within ref cell, and then send method will be able to modify sent messages to store the messages we've written. Okay, we'll store the sent messages. The sent messages is here, a vector. within ref cell. And then send method will be able to modify. Send method will be able to modify this part. Okay, let's see. Oops, my mouse is jumping again. Sorry for that. Signal. Here. So vect string is essentially wrapped inside ref cell to fix the issue. Okay, can do that. It's easy. Just wrap this with ref cell. This. Okay, but the ref cell is not in the preload, so use std. Where is it stored? Cell ref cell. Yeah, so it means that this one should be inside ref cell also. Ref cell. Or is it correct? Is it correct? Should be enclosed. Ref cell new. In this case, it's ref cell new. Ref cell new. So initializing the vector using the vector macro contains empty to ref cell. What is wrong here? Use borrow mut to mutably borrow vec string, panicking if any borrows exist. Borrow mut. So we need to implement borrow mut. Okay. Borrow mut. This is the one with the issue. This is the one which fixed the issue. So three main areas that were changed here in the struct. We are wrapping vector string to ref cell, and here when we are constructing, okay, there's this new function to create the mock messenger. So ref cell using the new function also to create the vector. And then here sent messages. Since it's immutable, so you do this borrow mutable. Then here assert equals we have it in the test. I think here you also need to do a what? Borrow what? Oh, not borrow mut, but borrow. Okay. It's the difference. What is the difference? Let's see. What's the difference? Okay, for the implementation of send method, the first parameter is still an immutable borrow of self, which matches the trait definition. We call borrow mut on the ref cell back in self-sent messages to get a mutable reference to the value inside ref cell. Okay, this one, which is the vector. Then we call push. Okay, the last change we have to make is the assertion. To see how many items are in the inner vector, we can borrow on ref cell to get an immutable reference to the vector. Okay, it's only borrow because it's an immutable reference to the vector. Now you have seen how to use ref cell. Let's dig into how it works. Keeping track of borrows at runtime. Wait, let's run this first. So we can run specifically, okay, all tests are this one. Okay, of course, you pass. When creating immutable and mutable references, we use the ampersand and ampersand met syntax respectively. With ref cell, we use borrow, okay, borrow for the counterpart of this one, and borrow mut for counterpart of this one. Methods which are part of the safe API that belongs to ref cell. The borrow method returns the smart pointer type reft. Borrow mut returns the smart pointer type refmut. Both types implement deref, so we can treat them like regular references. Reft borrow. Okay, maybe you can check. Borrow returns. Yeah, so here, yeah, borrow returns ref t, while borrow mut reference mut. Okay. Both types implement deref, so we can treat them like regular references. The ref cell keeps track how many reft and refmut smart pointers are currently active. Every time we call borrow, the ref cell increases its count on how many immutable borrows are active. When ref t goes out of scope, the count of immutable borrows goes down by 1. Just like compile time borrowing rules, ref cell lets us have many immutable borrows or one mutable borrow at any point in time. Okay, so ref cell lets us have many immutable borrows. So since it's many, ref cell increases its count of how many immutable borrows are active. If it goes out of scope, the count of immutable borrows goes down by 1. Okay, so ref cell, since you have many immutable borrows, when you borrow, it increases. When it goes out of scope, it decreases. Or one mutable borrow at any point in time. So mutable borrow is only 1. Mutable borrow is only 1. Okay. So which one is mutable borrow? This one is mutable borrow. Only 1. It is mutable inside this one. Messages. Send messages stores vector. Okay. Essentially the send messages is the vector. Only 1. But here Why is it send message borrow? Because mock messenger is no, mock messenger is immutable. Borrow, okay. Let's read further. Maybe we'll get more clarity in the next one. If you try to violate these rules rather than getting a compiler error as you would with references, the implementation of ref cell will panic at runtime. Listing 15-23 shows a implementation of send. Okay, here we're deliberately trying to create two mutable borrows active for the same scope. Okay, where is it? Implement messenger. Okay. For mock messenger. Messenger. For mock messenger. Okay. So if in send we have one borrow, self sent message borrow mut. Okay, so you're borrowing one here. Messages. Okay, because the condition for borrow mutability is only one mutable borrow at any point in time. Okay, so by doing it, the second one, of course it will complain. Let's copy this, put it here, then copy. Yeah, so no compile time because this is at runtime. Okay, if we run the test to send, no, which one shall we? Cargo test. Yeah, so one failed. Running test sends borrow. Okay, here it panicked. 6453. 64, line 64, column 53. And this one. Borrow mut. So it's not allowed. But if we comment this out, of course, it will compile. But when we run cargo test, there's no panic. It will not panic. Okay, so that is clear that borrowing a mutability, something mutable, you can only do once. Okay. Oops, my mouse is jumping again. We create a variable 1 borrow, okay, 2 borrow. So by commenting this out, of course, it will fix the issue. Notice that the code panicked. Yes, we saw the code panic. We saw borrow mut error here. Yeah. This is how refcelt handles violations of the borrowing rules at runtime. Choosing to catch borrowing errors at runtime rather than compile time, as you've done here, means you would potentially be finding mistakes in your code later in the development process, possibly not until your code was deployed to production. Also, your code would incur a small runtime performance penalty as a result of keeping track of the borrows at runtime rather than compile time. Oops. your code will incur a small runtime performance penalty as a result of keeping track of the borrows at runtime rather than compile time. However, using refslt makes it possible to write a mock object that can modify itself to keep track of the messages it has seen while you're using it in context where only immutable values are allowed. You can use refcell despite its trade-offs to get more functionality than regular references provide. Okay, so just reflecting a little bit, this part, your code will incur a small runtime performance penalty as a result of keeping track of the borrows at runtime rather than compile time. So having all these checks at compile time is better. But by using this, you get more flexibility in testing the code. You can create mock objects that can modify itself to keep track of the messages it has seen while you're using it in a context where only immutable values are allowed. You can use refcell despite its trade-offs to get more functionality than the regular references provide. So the use case is more on creating mock objects. Okay, so that is clear now. Allowing multiple owners of mutable data with RC and refcell. Multiple owners. Okay, multiple owners. So the reference counting, something to do with multiple owners. But this time it's in combination with immutable data, so we use refcell. But refcell is only one mutable data. Okay, I think that should be fine. Because RC here is referring to multiple owners. Okay. A common way to use refcell is in combination with reference counter or RC. Recall that RC lets you have multiple owners of some data, but it only gives immutable access to that data. Yeah, so the diagram here, that's every time we hear RC, let's visualize this diagram. You can have multiple owners, but the data is immutable. Okay, let's go back here. Okay. Recall that RC lets you have multiple owners of some data, but it only gives immutable access to that data. If you have an RC that holds refcell, you can get a value that can have multiple owners and that you can mutate. Oh, cool. For example, recall the cons list example in 15-18 where we use RC to allow multiple lists to share ownership of another list. Because RC holds only immutable values, you can change any of the values in the list once you've created them. Let's add in refcell for its ability to change the values in the list. 15-24 shows that by using refcell in the cons definition, we can modify the values stored in all of the lists. So what have we learned in using refcell? It's wrapping the value, the immutable value. Yeah. So this is the implementation. Let's check in our code how we modified it before. What we have is my box. No, we were using my box. Where's the ref C? Oh, this is not even ref C. Ah, list is here. List RC, RC list. Okay, C smart pointer, D custom smart pointer. Okay. Okay. So it means that in the list, yeah, we have RC. RC. That was already RC before. No? Was it RC? Yeah, it's RC. But we need to wrap this in ref cell. Ref cell. And then why are we having RC here again? Why are we having RC here again? Ref cell RC value new ref cell. Okay, ref cell new 5. RC new. I think we had RC new 5. Because this one we're using my box. So this is the similar to box T implementation. Okay. So what we can do is to comment this out. And we copy this. Consent name should be there. Do we have it? No. Here. Consent name RC. Now we need to add the use std ref cell. Where was it? Cell. Ref cell. Okay, there. So list RC ref cell. And then in main, RC new value. Okay, RC new cons of RC clone at value. That value. RC new nil. So this is A. Then in B, we have cons RC new. Because RC new ref cell, this part is actually this one. 3 RC clone. Yeah, in this part. RC clone over some A. Okay, so let's just copy this. Here. And let's go to line 85. Comment this out. This one is dereference. So value borrow mat. Okay, so borrow mat will the value is okay. So the asterisk we are unwrapping is like we're extracting value from RC new. Then borrow mat is actually ref cell, which we get the value 5. Yeah. And then we're incrementing it 10. Where is the value? Value in here. Okay, so it means that the value in A plus equals, so it becomes 15. A is 15, B is okay, A is here, so 3 and 15. And then here 4 and 15. 4 and 15. Okay, let's print this one. Let's see if we're doing our, we are the compiler, and see. At runtime, let's see. Okay. This is, it's a warning. It's a warning. Yeah, correct. It's 15, 15, 15. Yes. So somehow we understood something, which is good progress. Yesterday, I didn't understand anything at all. But that's how it goes. We learn step by step. Okay. We create a value that's an instance of RC ref cell and store it in variable name value. Okay, so this is the part where we are tracing this. We wrap the list A in RC T so that when we create list B and C, they can both refer to A. So RC clone, even if it's clone, there's no performance overhead, performance impact. It's just counting the references. We want to add 10. So adding 10, we are changing. So first step here, because it's wrapped in RC, so you dereference it. And then once you have ref cell, you do a borrow mut is equals to 5 plus 10. And that's what we get. Okay. Where's the operator? In chapter 5, dereference RC to the inner ref cell value. The borrow mut method returns ref mut smart pointer, and we use the dereference operator on it to change the inner value. Okay, yeah. This technique is pretty neat. By using ref cell, we have an outwardly immutable list value, but we can use the methods on ref cell that provides access to its interior mutability, so we can modify our data when we need to. The runtime checks of the borrowing rules protect us from the data races, and it's sometimes worth trading a bit of speed for this flexibility in our data structures. Note that ref cell T does not work for multi-threaded code. Mutex T is a thread-safe version of ref cell. Oh, there's another one, Mutex T. Okay, so in chapter 16, let's continue. Reference cycles can leak memory. Oh, Rust memory safety guarantees makes it difficult, but not impossible, to accidentally create memory that is never cleaned up, known as memory leak. Preventing memory leaks entirely is not one of Rust guarantees, meaning memory leaks are memory safe in Rust. We can see that Rust allows memory leaks by using RC and refcell-T. It's impossible to create references where items refer to each other in a cycle. This creates memory leaks because the reference count of each item in the cycle will never reach 0, and the values will never be dropped. Can never reach 0, and the values will never be dropped. Creating a reference cycle. Okay, so it means that a reference pointing to another one in a loop. Okay, let's look how reference cycle might happen and how to prevent it. Starting with the definition of the list, enum and trait. enum, list enum, and tail. Okay, we have, where's the list? Okay, list is here. You have tail. This one will return option referencing ref cell containing RC list match self. Okay, because it's option, so it can return cons or cons. Okay, if it's cons item, then option will be some, or option will be none. So where's the cycle here? We're using another variation of list definition in the second element in a const variant. Now ref cell RC list, meaning that instead of having the ability to modify I32 value as we did in 15-24, we want to modify list value a const variant is pointing to. We're also adding a tail method to make it convenient for us to access. Second item, if we have const variant, oh, I think this is another complex topic. Okay, so I think let's end here for now. Even this topic here is already quite heavy. It's not easy to digest. Perhaps tomorrow we come with a fresh mind and we'll go through these reference cycles once again. All right, so thank you so much for accompanying me today. I hope you learned something. And before I finally end, let me thank my supporters.